So this evening we begin on our study for phasors. Okay, we're going to talk about phasors and impedance. So to set us in context, we are now entering the realm of AC analysis, okay, alternating current. And we've already talked about this. We already touched upon this since last week. Okay, so what were we doing last week? We were busy training you how to write phasors, which is essential because we need to use that knowledge this week. So phasors is always used in AC analysis, and I'm gonna straight away get you to the 3 steps of how to tackle problems related to phasor analysis or AC analysis. So when you see any current source which has a alternating nature, for example, a sine or a cosine, here are the steps. So step 1, change, or rather convert. Sorry, just use a better word. Convert everything to a complex number. Okay, even if you don't get it first, it's okay. Just take this cookbook recipe with you first. So next, so after we convert it all to a complex number, we use familiar formulas to solve. Okay, and you'll see what I mean by familiar formulas. These are really not new to you already. So number 3, change all the complex numbers, or rather just change your answer, which is a complex number, back to normal. Back to normal. So, okay. So how your professor will call the first step is converting this to frequency domain. So your professor will call this frequency domain. Okay, converting everything to frequency domain. Okay, just for me to explain to you how to understand his language, this is called converting it to frequency domain. This one is calling it converting it back to time domain. Okay. Now there are some other formulas you have to know first, and that's why we're going to talk about impedance. So phasors, we already know how to write. So if you forget how to write phasors, or you haven't looked through how to write phasors, go back to my last video. I have it already uploaded. Now, what about impedance? Today, I will talk deeply about impedance. So again, I've already said that impedance is the complex version of resistance, okay? So you can think of this like resistance, but in the AC setting. Now, why do I say that? First, let us introduce to you the formulas for each of the impedance. So we have 3 devices that we need the impedance of. Number 1 is our classic resistor. The resistor. Number 2, we have the capacitor. Actually, let me just do inductor first. So our inductor. This is our inductor. And then number 3, we have our capacitor. Capacitor. So what is the formula for all these impedance? The impedance of each of their devices. Each of these devices. So let us take a look. So we just draw this table out. Okay. So for a resistor, the impedance of a resistor is simply its resistance. Oh yeah, I forgot to tell you. Impedance, we denote it with letter Z. So this, we denote it with the capital letter Z. So what is the impedance of each of the devices? The resistor, the inductor, and the capacitor. So firstly, for resistor, its impedance is simply its resistance. Yes, the impedance of the resistor is just equal to the resistance of the resistor, right? The resistance in the complex number is just its own resistance, okay? So that's pretty simple. Now, here are some formulas which are new to you. for an inductor, the impedance of an inductor will be J omega L. Remember, J is the complex unit, okay? So J is actually root of -1. We've already talked about this last week. We will not use I anymore because I stands for current when we do circuits. So it's J omega L. Omega is the radiant frequency of the AC source, right? Remember AC source, I can write it as the amplitude cosine omega t plus a phase. So this omega is this omega. Okay, so next we have the impedance of a capacitor. So the impedance of a capacitor is given by 1 over J omega C. Okay. Oh yeah, I forgot to tell you. In case you didn't know, L stands for the inductance of the inductor. So J again, this is root of -1. Omega is the radiant frequency of the source, and then C is the capacitance of the capacitor. So this one is J omega L. This one is 1 over J omega C. There's also an interesting trick related to complex numbers that I want you to know for the capacitor. So you see, I'm just going to show you. So 1 over J omega C, there's a trick you can do to transfer the J to the top. So the trick is like this. Multiply top and bottom by J. So multiply top with J, bottom with J. Now what do you get? See, J times J is -1, correct? Because root of -1 times root of -1 is just -1. Okay, so this times this gives me negative on the outside. And then this 1 times J is just J. So if you want to remember the formula like this, it's fine also. I prefer to remember it like this, and then I just do this when I need it. Yeah. But I'm telling you this trick, right? Because we need this for tutorial 8, I think. Yeah. So just keep in mind of this trick. We will come back and use it in tutorial 8. Okay. So that's it. Yeah. So you have to remember this table because these are not provided to you. So the impedance of the resistor is its own resistance. The impedance of inductor is given by J omega L. Impedance of capacitor is given by 1 over J omega C. Remember these 3 formulas, and then we will now move on to explaining this table. So other than that, okay, so let me explain step 1. Step 1, they say change everything to complex number, right? So when you see phasors, oh sorry, when you see sources, sources, you change them to phasors, which we already learned from last class. And when you see for example, you see resistors, capacitors, or inductors, you change them to impedance. Okay, you use the formulas that we already talked about. So I'm going to repeat again. Change everything to complex number means when I see sources, change them to phasor. When I see resistors, capacitors, or inductors, change them to the impedance using the formulas that I mentioned just now. Okay, next, use familiar formulas to solve. Now, what do I mean by use familiar formulas? You've already seen this, and we've already touched upon this many times in earlier classes. So let's start with this. There's a formula related to the phasor volts and the phasor for current and impedance. Does this look familiar to you? What does this look like? This looks like Ohm's law, correct? Ohm's law tells you V is equal to I times R. And this is the same thing, but now all of them are complex numbers. You see, remember this is capital V. Capital V is phasor, and phasor is a complex number. Capital I is also a phasor, it's also a complex number, and Z in general can be a complex number. Okay? So you see, this formula looks like Ohm's law. So it's really familiar to you already. Okay, so this is what I would say is the Ohm's law for AC. Okay. Now, what other formulas are also familiar to you? So Remember, total resistance for resistors in series is given by R total for series is given by R1 plus R2 plus dot dot dot. Well, for total impedance in series, Z total in series, it is given by Z1 plus Z2 plus Z3 plus so on. See, they're the same thing. And we can also extend this to parallel arrangement. Okay, it's not like this, sorry. 1 over Z parallel, I'm just going to call it para. So 1 over Z para is equals to 1 over Z1 plus 1 over Z2 plus 1 over Z3 and so on. So they're also following what we've already known since secondary school, correct? And that's why I say, once you convert all these to complex numbers, right? So you change the sources to phasors, you change RC and L into impedances, then everything becomes quite familiar to you already. It's all a matter of knowing how to use your calculator for doing these complex number calculation. Okay, so that's it. That's what I mean by using familiar formulas. So all that you have learned before can be used for impedances and phasors. Next, and the final step is change complex number, and usually this is your solution or your answer. Your final answer, you just change it back to normal. And we've already learned how to change it back to normal, right? Last class, we already learned how to change from time domain, which is the normal AC source, in the form of A cos omega t plus a phase. We already know how to change this to this. And we also know how to do the reverse. So now step 3 is the reverse, is this red arrow from the complex number back to the real number. So that's what I mean, change it back to normal. With that being said, let's just start to do some examples. So, okay. So let us try this. I will go through 2 questions and that will be the end of the day. So let's just see how simple this is. So we're given this source, actually it's an AC source because you see it's cosine, right? So it's sinusoidal. So by right, I should denote it like this. Sorry. And then we have a series arrangement of a resistor, an inductor, and a capacitor. So step 1 is change everything to a complex number. So let us change the source to a complex number. Oh, sorry. Let me define the problem first. The problem that we want is to find the current through this circuit, okay, which is given by IT. Okay. So step 1, change everything to a complex number. Let us change Vs into a complex number. So we denote it with capital V S is equal to, now to write the phasor, remember, you just take the amplitude and the phase. So amplitude and the phase, 750 at an angle of 30 degrees. Okay, then what else can we change? So we can find the impedance of each of the devices, correct? So let us find the impedance of the resistor. The impedance of the resistor is given by the resistance only. So we'll just copy down 90 because that is the resistance. So that must be the impedance for the resistor. Oh yeah, I forgot to tell you that the unit for impedance is actually just ohms. It's still ohms. Okay, so that's why I say it's a complex version of resistance. Next, we find the impedance of the inductor. So ZL is given by, remember the formula? The formula is J omega L. So J times, now the omega is given by this omega here inside the cosine function. So that is 5,000. So we take 5,000 times, the inductance is 32 millihenries. So we see milli, we need to change it back to normal. So times 32 times 10 to the power negative 3. Okay, so that is J omega L. Now let us compute this using our calculator. So let me just take this out. So J is given by I times omega is 5,000 times 32 times 10 to the power of -3. So we get 160J. So this is actually ZL is given by 160J. Then we want to find the impedance of the capacitor. So remember, impedance is given by of the capacitor is 1 over J omega C, which is 1 over J 5,000 radians per second times the capacitor is 5 times 10 to the power of -6, if I remember. 5 microfarads, correct? Yes, 5 microfarads. So let us calculate this answer. So 1 over J times omega 5 times 10 to the power of -6. So that is -40J. So ZC is given by -40J. Now, what do we want to do? We want to find the current through here, right? So let us use the Ohm's law, but for phasors. So Ohm's law says that V, which is this Vs, so V is equal to IZ, correct? So this V is this V that we got here from the start. Okay. So 750 at an angle of 30 degrees is equals to, the I is what we don't know. Okay. The I is what we want to find out. So I times the Z, this Z is actually Z total. Okay. So it is the total impedance of these three devices, the resistor, the inductor, and the capacitor. So we need to total them up. Now, the question is, what is their arrangement? You see, their arrangement is in series, okay? I hope you can see that they're all in series with each other. So to find the Z total, so let us find Z total. Z total is given by, first, the resistor, plus the inductor, plus the capacitor, which we've already found out from just now, right? So 90 ohms plus 160 J ohms plus, sorry, I think it is, oh yeah, plus minus 40 J, minus 40 J. So if you add this together, you get 90 plus 120 J. So you can just leave it in rectangular form first. So this is your Z total. Now we will substitute this into our formula. So substitute this into here. So let me rewrite this. Okay. Let me just write it down here. So V equals to I Z total. This V is what we got just now, which is 750, 30. So 750 at an angle of 30 degrees is equal to I, we don't know, times Z is 90 plus 120J. 90 plus 120J. Now we move this over, so divide. So to get I is given by 750 at an angle of 30 degrees divided by 90 plus 120J. Okay, so let us calculate this answer. Okay, what did I write? Okay, this is what I want to find out. So 750 at an angle of 30 degrees, 90 plus 120J. We compute this, but this is in rectangular form. We want to change it to a phasor form. So that means we have to convert this to polar. So you take your answer, and convert it to polar form. Okay, convert it to polar. We get 5 at an angle of 53. So let me just draw that. So 5 at an angle of negative 23.1 degrees. So this is our phasor form. We want to change it back to the time domain. So just write it back to normal. So 5 cosine. Now, our omega is borrowing the omega of the voltage source, correct? Which is 5,000. So we just copy the omega of the voltage source. So it will be 5,000 T minus 23.1 degrees. And that is our answer. This is our answer. This is IT. Now let me check if the answer is correct. Yes, 5 cosine 5,000 T at an angle of negative 23.1. Okay, so that's the answer. Quite simple, correct? Yeah, it's really just using what we've already known since years ago. Okay, so this is the series arrangement. Let me move on to show you what the parallel arrangement will look like. And again, it's nothing scary. So let me hold on. Okay. So again, let us use our 3 steps. Number 1, change everything to complex. Number 2, use the familiar formulas. Number 3, change it back to the time domain. In other words, write it back as a cosine function. So in this problem, we are given a fluctuating current source, which is AC, and we are expected to find the voltage source across this. Now, the voltage source across the terminals of the the current source is the total, so to speak, total potential difference of the whole circuit. Okay, so never mind that. Well, what that means is actually I need to combine all these impedances together. Okay, then I can evaluate what is V. In this case, capital V. Okay, capital V. So number 1, change everything to complex numbers. So first, let us change the source. Now, the source I denoted with capital I equals to the amplitude is 8. Now, what is the phase? You see, the phase is nothing, right? It's nothing. I can write this as 8 cosine 200,000 T plus 0 degrees, correct? It's just the same thing, plus 0 degrees. That's why the phase is just 0. Okay? Next, I now need to find the impedance of each of the devices. So for the resistor, it is just its resistance. For the, okay, here we have a resistor. So ZR. Let me be specific, okay? Because there are 2 resistors. So let me call this Z10 ohms. Let me call this Z6 ohms, which is 6 ohms. Other than that, we have the inductor. So Z of L is again given by J omega L. J times omega 200,000 times L is 40 times 10 to the power of negative 6. So let me just calculate this. 200,000 times 40 times 10 to the power of negative 6 is 8J. Okay, then ZC is given by 1 over J omega C, which is 1 over J 200,000 times 10 to the power of negative 6. It's actually 1 times 10 to the power of negative 6, but I just omit the 1. So let me just compute this. So 1 over J times 200,000 times 10 to the power of negative 6. So it's negative 5J. This one here is negative, sorry, this is C. This is C. Yeah. Oops. So this is C. This is L. Then this is negative 5J. Okay, so now we already converted everything to complex numbers. We can use our familiar formulas. Now, how to simplify this circuit? How to get the total impedance of all these devices? Now, let us look one by one in each branch and see if I can simplify anything. So, the first branch, it's already quite simple enough. There's only just one resistor. Now, look at the second branch. The second branch, I can combine it, correct? Because there are two separate devices, which is the resistor and inductor. So I can combine them together. So let us find the total impedance of this branch. Let us call this total as ZA. Okay? So to find ZA, because the resistor and the inductor are arranged in series, we can just add them together. Okay, add the impedance together. So I'm going to evaluate it here. ZA is given by Z 6 ohms plus Z of the inductor, which is given by 6 plus. Now, what is the inductor again? 8J. And this is the total resistance of ZA. Now, let's look at the third branch. The third branch is just itself, the capacitor itself, so it's already simple enough. So, let me redraw this arrangement. So here, you have the capacitor. Then now we have this new ZA. ZA. Here's the source. Okay. The source is what? 8. 8 at an angle of 0. This is 8 at an angle of 0. And then this resistor is 10 ohms. 10 ohms. And ZC is negative 5J. Negative 5J. So, let me ask you all this. These three devices, what's their arrangement? Series or parallel? Let's check the chat. So, Vishnu, Samuel, Ain, Raymond, what's the arrangement of the three devices? Series or parallel? Okay, we got a message. Let's see. It is parallel. Okay, Hamza has a very unique way of showing it. Yes, they're parallel. Okay, they are parallel because they are all connected to the. Sorry, they're all connected to the same node. Okay, let me get my charger out. Low battery. Okay. Thank you, Hamza. Yes, all of them are connected to the same nodes at their two ends, right? You see, this end, and this end, and this end, and then this end and this end, all of them are connected to the same node, which is this node, this node, this node. So by definition, they are parallel. Okay. Now we want to find the total impedance in parallel, correct? So we'll just use the formula that we already know. So 1 over Z para is given by 1 over Z 10 ohms plus 1 over ZA plus 1 over ZC. Then this is 1 over 10 plus 1 over, now what's our ZA? ZA is 6 plus 8J. 6 plus 8J plus 1 over ZC is ZC is negative 5J. Negative 5J. So let us compute what is this answer. Okay. So 1 over 10 plus 1 over 6 plus 8J, oops, 6 plus 8J plus 1 over negative 5j. Negative 5j. Find this answer. Okay. So what's the answer? The answer is 4 over 25 plus 3 over 25. So 4 over 25 plus 3 over 25j. But if you want to find, so if you want to find z parallel, right, then we take the reciprocal of this, right? Take the reciprocal of this answer. So z para is equals to 1 over this answer plus 3 over 25j. So let us do that. Go back to my calculator. I take 1 over answer. I'll get 4 minus 3j. So this answer is 4 minus 3j. Now this is my total impedance of this circuit, right? I've already combined all of these three devices. I combine all these three devices into one single impedance, which is like this. So now I redraw it like this. This is the current source. And then after I combine it, it becomes like this. So this is Z para. Yeah. So to find the the current through this circuit, I just use Ohm's law. So V is equal to I Z. V is what we don't know. I is 8 at an angle of 0. And Z is 4 minus 3j. 4 minus 3j. Okay, let us calculate that. So 8 at an angle of 0 times 4 minus 3j. So 4 minus 3j. I get this answer, but I don't like it in rectangular form because this is a source we're talking about, so I need to change it to phasor. So I take my answer and then I convert it to polar. So take this, complex, then change it to polar. Okay, I get this answer. So what's the answer? 40, negative 36.87. Okay. So after I find this, 40 at an angle of negative 36.87 degrees. Then I just change it back to the time domain, which is just writing it like normal time. So therefore, my answer is V of t is equal to 40 cosine. The omega was what? The omega, we just borrow it from the source. So the source says 200,000. Okay? So cosine 200,000 t at a phase of negative 36.87 degrees. Now let me check if our answer is correct. Yes, the answer is correct. So 40 cosine 200,000 t minus 36.87 degrees. So that's basically it. Yeah. So we've covered what we need to cover for today. That is AC analysis. So when you're given an alternating current source, be it an alternating voltage source or alternating current source, you just follow the 3 golden steps. In this case, change everything to complex numbers first. So wherever you see a phasor, wherever you see a source, change it to a phasor. Wherever you see resistors, inductors, capacitors, change them to impedance. Okay, so you have to remember all those formulas. The table that I showed you just now, you have to remember that. So for resistors, the impedance is this resistance. For inductors, it's J omega L. For capacitors, it is 1 over J omega C. Okay, having convert everything to complex numbers, you can now use formulas that you are already familiar with. Okay, Ohm's law, total impedance in series, total impedance in parallel. You solve the problem, and then after that, remember, at the end of the day, you want it in time domain, right? You see, all of these are asking for a time domain. But I think in the past year papers, right, they often ask for leaving your answer in phasors. So just follow what the question wants, okay? So if they ask for a phasor, you just leave it as phasor. But by default, we are more interested in the time domain form of the answer, okay? Which is the cosine and the sine that we all know and love. And that is basically it for tonight. Yeah, so I can just end the recording here.